Good evening, everybody. I've just been given the signal that we can start, and it's a really great pleasure to welcome you all here this evening to the inaugural lecture of Professor Greg Wildgoose from the School of Chemistry. It's great to look around the audience and see many of our colleagues, students, people from the city, and of course members of Greg's family as well. You all are very, very welcome. To the man of the moment himself, Greg grew up in a former coal mining village near Chesterfield and was actually the first recipient of a Professor David Walker scholarship. And this enabled him to attend the old Swinford Hospital School in Starbridge. He then went on to read chemistry at St John's College in Oxford and was awarded a scholarship in 2002. Between 2003 and 2006, Greg remained at Oxford to study for his doctorate in chemically modified nano-electrochemistry. And this was actually done under the guidance of his very influential mentor and role model, Professor Richard Compton. Then in 2006, Greg was elected as a junior research fellow in St John's College, again in Oxford, where he continued to work in the Compton Group. Then in 2009, Greg was actually awarded a very prestigious university research fellowship by the Royal Society. And he elected to establish his independent research group, not in Oxford, but here at UEA. And I think that has been to the great advantage of UEA over the years since he's been with us. At the point that Greg moved, he took a very brave and indeed quite unusual decision, and that was to shift the focus of his research into a new area, to move away from the study of nanomaterials for electroanalytical chemistry, and to instead focus on synthetic chemistry, small molecule activation, and molecular electrocatalysis for energy applications. It is brave to shift your research, and when you do that, you do sometimes need some help and some encouragement from other colleagues as well. And Greg asserts that this key change that he made at the time was made possible in large part by the support he received from his colleagues here in chemistry at UEA, and also from one of his collaborators and good friends, Dr. Andrew Ashley in Imperial College. It was the right decision to make. Greg's research has gone on from strength to strength, and in 2012, Greg secured a 1.3 million euro European Research Council starting grant. These are really very prestigious grants that only go to the very top scientists. Absolutely justifiably, he was promoted to reader around that time, but perhaps most importantly, I gather in 2012, he married his then partner of 9 years, Juliana, and these are definitely the most important things that we do. In 2014, Greg was elected as a Fellow of the Royal Society of Chemistry, again, another very, very prestigious award. And this was in recognition of his services to advancing chemical research. And at that time, he also took on an important role for us here in the university, and that within the School of Chemistry was as Director of Enterprise. And then, back in August 2015, he was promoted to Professor of Chemistry, which of course has led to him being here today to give his inaugural lecture. Now I think it's clear from everything I've said so far just how strong, how prestigious the research that Greg has been doing is. It's illustrated by the research grants that he's won, by the European Research Council starting grant, for example, but also by the many high-quality scientific papers that he's published, well over 100 very, very high-impact papers so far, many more to come, I know. He's published a book chapters, numerous patents. One of those patents has led to the founding of a $14 million company, Sonova Systems Incorporated, based in California, in developing new pH sensing technology. His research has been cited over 4,000 times over the last 13 years or so. And he's also become associate editor of a journal, the Royal Society of Chemistry Advances. He's won awards, including the Best Young Energy Storage Scientist Award from the European RS2E network, That's for his novel concept of frustrated batteries. Now, as Vice-Chancellor of this university, I really am very proud of all of the work that our colleagues at UEA do in undertaking important research to help find solutions to major global challenges. Challenges around the study of nutrition, around ageing populations, around water security, climate change, international relations, and many other areas. And Greg's research seeks to address one of the greatest challenges we face today, and that's the need to secure clean, renewable energy sources for the world's growing populations. As Director of Enterprise in Chemistry, he also shows how we can take the leading research that we do here at universities and harness that creative thinking, that innovation, to actually then go on and apply it in these important global areas to make real-world impact. And I fully anticipate that what we're going to see today is a lecture that shows us that real-world impact that Greg's making. So without further ado, I'd like you to join me in welcoming Greg to deliver his inaugural lecture. Please, Greg.
Thank you very much, Vice-Chancellor, for those kind words of introduction. First things first, can everybody hear me okay? Yeah? Brilliant. Right, so tonight I'm going to be talking to you about the power of frustration, how we are developing ways to power things like these, using molecules like these, based on a clean, renewable energy vector. And I am a chemist. Right? This is going to be a chemistry lecture, so I make no apologies that there will be some chemical equations in this lecture. And when I talk to people who aren't chemists, quite often they tell me they were put off chemistry at school by their teachers and so forth, and they seem to think that chemistry is all about this, the periodic table, and learning random facts about all these different elements and so on. So let's make sure we start off on the same footing. Chemistry is the central science. It underpins much of biology, much of environmental science, much of geology, volcanology, medicine, engineering, and materials. And you can't really have a science department without having somewhere a chemistry department. And chemistry is the study of matter. It's the study of everything around us. The bodies that we inhabit, the food that we eat, the water we drink, the air we breathe, the houses we live in, the cars we travel in, the gadgets we play with, the seats that you're sitting on right now. They're all chemicals. It's all chemistry. And because it's such a vast topic, we divide chemistry into what I call the 3 pillars of chemistry, sub-disciplines within it. And there is physical chemistry. Okay, that's the chemistry of energy levels within molecules, the energy driving reactions. It's the study of how fast those reactions go, the rates and the kinetics. It's the study of how matter interacts with light and magnetic fields and electric fields. And it's also the study of how matter interacts with other bits of matter, the forces between molecules and so forth. Then there's inorganic chemistry. Right? That's the chemistry of how the world we know is made up of all the different combinations and permutations of these 118 or so different elements, and how we, as chemists, can combine these elements to make ever more useful things and materials. And finally, there is organic chemistry. That's the chemistry of just one specific element, the rich chemistry of carbon-containing molecules and compounds. And that includes the chemistry of life itself. All life on Earth that we know of is carbon-based life forms. And normally as a scientist, you would, through your training, specialize and specialize and specialize into one of these sub-disciplines that you choose. But what I'm hoping to show you tonight is that when we try and tackle the really big problems, the really big challenges that we face, we have to draw from all the different areas that we can. But I didn't know that when I was an undergraduate, so when I went off to university, I was convinced that I was going to become a synthetic organic chemist, which may come as a little bit of a surprise to some of my colleagues. But then I met the first of 2 people that I want to introduce you to tonight. Unfortunately, they couldn't be here in person, who completely changed the course of my scientific career and indeed many aspects of my life. And the first of these is Professor Richard Compton. Now, Richard is a world-leading electrochemist, and I'll explain what an electrochemist is in just a moment. But at this point in the story, more importantly, he was my tutor in physical chemistry when I was at university. And one Friday afternoon, he decided to have his tutorials in his other office, also known as the Lamb and Flag, which is a pub next door to St. John's in Oxford. And after plying me with far too many beers, Richard suggested that I might like to work in his research group over the summer vacation and get a feel for the kind of research he was doing. And so I did, and I loved it, and I was hooked. And after that, I wanted to become a physical chemist, an electrochemist. So, what is electrochemistry? All right, well, synthetic chemistry is all about making and breaking chemical bonds. Right? And these reactions are often driven by things like heat, or light, or stirring, or pressure. And whenever we have these reactions as chemists, we draw these reaction mechanisms to show what's going on, and they've got all these curly arrows whizzing around everywhere as we make and break different bonds. And each of those curly arrows fundamentally represents the movement of a pair of electrons. Right? Electrons are negatively charged. Moving charges equals an electric current. So electrochemistry is simply the study of chemical reactions driven using electrical energy, of voltage, as the driving force. So in 2 slides, I'm going to teach you all you ever need to know about electrochemistry to understand this lecture. Right? If we add electrons to a chemical species, that's called a reduction. Right? So I can take some iron 3+, I can add an electron to it, and I will reduce it to form iron 2+, right? I've decreased the oxidation state from +3 to +2. Conversely, if I take an electron out of a chemical species, that's called an oxidation. So I can go backwards. I can take an electron out of iron 2+ and form iron 3+. And together, these reduction and oxidation reactions are called redox reactions. So what we do is we take our experiment. Here we've got something of interest. This solution at the start of the experiment was orange, because it's an iron 2+ species. And we place into it an electrode. That's just a conducting bit of metal or a conducting bit of carbon. We put 2 other wires in there to make a circuit. And then what we do is we apply a voltage to that electrode. And we sweep the voltage along until eventually we get to a value where we switch on that redox reaction. And we start to get a current flow. And now we are oxidizing the orange iron 2+ and forming this blue solution of the iron 3+. And if we scan in the opposite direction, eventually we get to a value where we switch on the reduction reaction. So now we get a current in the opposite direction, and we're reducing iron 3+ to iron 2. Now, the size and the shape of those peaks tells me about how fast those redox reactions are and about any other chemistry that's going on alongside those electron transfers. And the position on the x-axis, the voltage of that redox reaction, tells you about how much energy you need to put in to drive that reaction. And the aim of the game for this lecture is we want to make these peaks get bigger, right, and move to the left. In other words, we want to get more current out by putting less energy in. So, off I went in Richard's group, and I stayed there, did my doctorate, and then I did my junior research fellowship in the same group. And I had the start of a really budding career. I'd published lots of papers and some patents in a spin-off company, and I started to get an international reputation as a physical electrochemist specializing in nanomaterials. And then one day, I got an email from the second person who was going to change the course of my career. Dr. Andrew Ashley, who's currently at Imperial College. But back then, we were undergrads together at Oxford, him at Christ Church College, me at St. John's. And he studied his doctorate in Oxford, specializing in synthetic inorganic chemistry. And then we became junior research fellows together, him at Balliol College, next door to St. John's, where I was. And now we're both university research fellows together as well. And Andy is a leading expert in Lewis acidic boranes, right? We're going to be talking a lot about those later on in the talk, and I'll explain to you what that means. But when I got this email, I said, yeah, sure, Andy, let's meet up in my office. So we went to the Lamb and Flag. And over many meetings and many, many beers, Andy started to explain to me all about his world of synthetic inorganic chemistry. And the more he explained to me, the more I understood his language. And I started to explain to him all the things that electrochemistry could do for him, and the more I told him, the more he understood my language. And so we came together and we understood each other and we could work really well together. And so was born a collaboration that's now been going for over 8 years, I think. But when it came time for me to leave Oxford and apply for my university research fellowship, it was Andy who came up with the idea that I should switch research fields and I should become a synthetic inorganic chemist. So this is all Andy's fault. He led me into this. So there I was. I rocked up at UEA in 2009, 7 years ago, and my colleagues in the department were expecting to get a physical electrochemist specializing in nanomaterials. So I arrived on their doorstep and I said, hi, no. Despite having no background expertise or no skills or training or no knowledge of the prior scientific literature, I'm actually going to become a synthetic inorganic chemist, and I'm going to build a world-leading research group here doing that. And that would not have been possible without the support and the patience of Andy. I was on the phone to him every day, pretty much. He was telling me what not to do. And it wouldn't have also been possible without the support and the help and the generosity of some of my synthetic colleagues. And there are a lot of them, but I'd like to, in particular, thank Professor Manfred Bockman, Professor Simon Lancaster, and Professor Chris Pickett, without whom none of what I've done would have been possible. So whilst Andy and I were in the pub mulling over how we could work together, we were looking around and trying to think of what problem we could solve. Because that's what chemists do. We solve problems. And luckily for chemists, the world faces some pretty big problems. Now, I am not particularly interested in whether or not you as individuals choose to believe or disbelieve the growing mountain of evidence and scientific data that human activities, such as burning fossil fuels, are changing our environment. I'm not interested in that because the one fact that nobody is arguing with is that if we keep burning our fossil fuels, then eventually they're going to run out. And so then the question is, right, well, how do we keep the lights on and move people from A to B without using a horse and cart when all the oil runs out? And can we convince people to switch to whatever that is before we kill the polar bears, before it's too late? And here at the University of East Anglia, I'm part of a group of scientists from departments across the science faculty who form the Energy Materials Laboratory. And in the Energy Materials Laboratory, we believe in something called the hydrogen economy. Okay, hydrogen is a gas. It forms 98% of the known universe, and it's a fuel. You can burn hydrogen with oxygen and release energy. And when you do that, the only waste product you form is water. And you can make hydrogen from water simply by putting in some electrical energy from a renewable source and splitting the water to make hydrogen and oxygen. And to show you how easy it is to make hydrogen from water, where are we? Okay, here I've got a pot. Okay, and in that pot, I've got 2 wires connected to a battery. And there you can see bubbles coming off, right? Off of both wires, the one that's got the most bubbles coming off is producing hydrogen, and at the other wire, we're producing oxygen, right? It's dead easy to make hydrogen from water. And we live here, Earth, the blue planet. And it's called the blue planet for a reason. 70% of our Earth's surface is covered by water, and best of all, most of that water is salty and therefore conducts electricity. So, the question is, why are we, as a species, so addicted to burrowing into the Earth and digging up and then burning fossilized bits of solar energy, which is all that oil, coal, and gas really are? Well, enough energy falls from the sun to the Earth in one day to power all of our energy needs for an entire year. The answer to that question, the reason behind our seeming stupidity, is money. And to understand how money comes into play, you have to understand how we burn hydrogen. For those of you with a nervous disposition or pre-existing heart conditions, there's going to be an explosion, so brace yourselves, okay? There are two ways you can burn hydrogen. There is hot combustion, right? Smoke alarm, fire alarm, no? Good. And if you've ever been to North America, you will appreciate that over there they like to do things bigger and better than us usually. So this is how Americans burn hydrogen.
10, 9, 8, 7, 6, start, 2, 1, booster ignition, and liftoff of the Space Shuttle Discovery, returning to the space station, paving the way for future missions beyond.
It's very dramatic. So that's one way to burn hydrogen. Then there's the intelligent way to burn hydrogen. It's called cold combustion. Instead of a loud bang and lots of flame and light and heat energy, okay, we simply divide the combustion processes into two spatially separated electrochemical reactions. So two electrodes. One of those electrodes we call the anode, right? And we're going to use that to oxidize hydrogen. We're going to take two electrons out of the hydrogen molecule and leaving behind protons. Then at the other electrode, which we call the cathode, we're going to combine those two electrons and two protons to reduce oxygen, and we form water. Right, so overall, hydrogen and oxygen in, water out, no big bang. Instead, we get electricity. And that's the origin of a hydrogen fuel cell. Right, so we've got our anode and our cathode. We put hydrogen in, we oxidize it at the anode. The protons go across the fuel cell. The electrons go round outside the fuel cell through a load, which will be the lights in your home or the motor in your car. And they come round the other side where we combine the electrons and protons with oxygen, and we produce water. All right, and this is where the money bit comes in. So the hydrogen fuel cells were invented before the internal combustion engine. This is Grove's first fuel cell back in 1839, and what he did was bubble hydrogen and oxygen over a series of platinum electrodes, and he got some electricity and a voltage. If we fast forward 176 years to a modern fuel cell, okay, the design's got a little bit better, and the materials that we use are a little bit fancier, but this layer here, this catalyst layer, that's still platinum. Right? Effectively, we're still using platinum electrodes. The chemistry hasn't changed, the technology hasn't changed in nearly 2 centuries. In the intervening time, the internal combustion engine has become incredibly powerful and efficient and lasts for a very long time and is cheap. And I think the reason that fuel cell technology has been held back for all this time is, and everybody knows that statement. Right? I hate everybody knows that statement, because everybody knows that 9 times out of 10 they're wrong. But every chemist and every chemical engineer from every university, graduating from every university in the world, will have been taught at some point that platinum is the best metal catalyst for hydrogen oxidation, and they'll have been shown some sort of plot like this. We call this a volcano plot. It's measuring activity against some parameters. And right at the peak of our volcano sits platinum. And it is true. Under laboratory conditions, platinum is the best metal electrocatalyst to produce or oxidize hydrogen. But is it the best catalyst for our application in a fuel cell? And I have no background in fuel cell technology, so I came to this with a fresh pair of eyes, and I looked at this as a chemist. Platinum is poisoned, stops working, by common impurities, carbon monoxide. That's ubiquitous in the hydrogen we use, because 95% of the hydrogen we make every year on Earth is not made from water, it's made from oil. So you have to purify the hydrogen to a very, very high degree before you can use it. And it's also poisoned by carbon dioxide, so if your fuel cell breathes air, then eventually it will stop working. And if I ask my synthetic colleagues in the audience tonight, if I turn around to you and said, I've made the best catalyst in the world ever for olefin polymerization to make plastics, but you've got to purify the feedstocks to 5 nines purity, 99.999% purity, before you can use it. They would laugh at me and say, Greg, you haven't made the best catalyst in the world, you've made the worst, and industry would never use it. But in the fuel cell community, purifying hydrogen to 5/9 purity is perfectly acceptable. Platinum is rare and therefore very expensive. And this is probably why we've been obsessing about it for 2 centuries. Humans tend to get obsessed by shiny, rare, expensive things. It gets worse, though, because there isn't enough platinum in the ground to put a hydrogen fuel cell into every moving vehicle currently on the planet. And that number of vehicles is set to double in the next 20 to 25 years. So even if we develop the best platinum catalyzed fuel cells ever, we can't use them for the application we want. There isn't enough of it. And it's not a selective catalyst. It catalyzes the hydrogen oxidation. It's also used in the fuel cell to catalyze the oxygen reduction. And that means we've got to separate the hydrogen from the oxygen using a thin and fragile and expensive membrane, conducting membrane. And to make that membrane conduct, we've got to keep it wet. So now we've got to purify our fuel gas, then we've got to manage and humidify and control the water going into and out of the fuel cell. And all along the way, we have compromised and compromised and compromised what was otherwise a quite simple technology and added all this complexity. And every bit of complexity we add is more expense and it's more sources of potential failure. So it shortens the lifetime of the fuel cells. All just so that we could use platinum, because it's the best catalyst. I'm not a great high thinker. I looked at this and I just thought, easy solution, just get rid of platinum. Wonder why nobody had thought of that. Carbon electrodes are cheap, readily available, and they already make up most of the electrode in the fuel cell. We're just not going to add bits of platinum to it. The problem is that hydrogen oxidation on a carbon electrode is very difficult. It requires a huge 1.5 volt driving force. So we're still going to need some kind of catalyst. And I'm not knocking platinum. There are some things when it catalyzes hydrogen oxidation it does really, really well. So I don't believe in reinventing the wheel. We're going to copy what it does well and just improve on it. Right? So we need a molecular catalyst that's going to work in a similar way to platinum. So that means it's got to pre-activate hydrogen by splitting that strong hydrogen-hydrogen bond. But it's got to be made out of cheap and earth-abundant elements, and whatever it makes by splitting this hydrogen has got to be easier to oxidize, to take the electrons out of, than hydrogen itself. So when Andy and I were working on this, we thought, well, okay, what we need are frustrated Lewis pairs. Now, to explain what they are, I'm going to have to teach you a bit more chemistry. In chemistry, a Lewis acid is defined as something that can accept a pair of electrons. For example, BH3, borane, right? This is borane, and it's got this empty orbital here on it, on the central boron atom, that can accept 2 electrons. Right? So a Lewis acid is an electron pair acceptor. So it makes sense that a Lewis base, therefore, must be an electron pair donor, like ammonia. Right? Ammonia's got this pair of electrons in this orbital here, which are not involved in bonding, and it's able to donate those. So if you mix borane and ammonia, right, they will react spontaneously. The nitrogen lone pair will donate into the empty orbital on the boron and form a chemical bond between boron and nitrogen. You form an ammonia-borane adduct spontaneously. And before I tell you about frustration, whilst we're talking about Lewis acids, I'd better introduce you to this one. This is tris-pentafluorophenyl borane, which is a bit of a mouthful. So we call it bar-15. This is the structure of bar-15. It's got a central boron atom in pink, right? 3 benzene rings attached to it, and every other position not bonded to boron has a fluorine atom attached. So the green atoms are fluorine, the grey are carbon, and the pink is boron. It's a strong Lewis acid. It's cheap and it's easy to make. And so Warren Peirce, who's one of the founding fathers of frustrated Lewis pair chemistry, described this as the ideal boron-based Lewis acid. So you're going to be seeing a lot of bar-15 in this talk, so that's what it is. So frustrated Lewis pairs were introduced to chemistry 10 years ago by the other founding father of FLP chemistry, Professor Doug Stephan at the University of Toronto in Canada. And the concept's very simple. Take a strong Lewis acid and a strong Lewis base and simply make the molecules too big and too bulky for them to be able to get close enough for them to react and form an adduct. Okay, and then the Lewis pair is frustrated. So this is bar 15. There you go, bar 15. That's our Lewis acid. Our Lewis base is an amine, right? This is tetramethylpiperidine, and that's what it looks like in 3D. And you'll see that this molecule is too big and bulky to ever get close enough to allow the lone pair on the nitrogen to donate into the empty orbital on the boron. And so it's frustrated. It doesn't form an adduct. However you might try. And this frustration equals unquenched reactivity. There is a driving force for the Lewis acid and base to react, but because they're too big, they can't. And so we can exploit that driving force, that energy. And so if we put a small molecule like hydrogen in between our frustrated Lewis pair, it will split the hydrogen apart unequally. So we'll have a H-, which we call a hydride. Right? That will go on the Lewis acid. And we'll form a H+, which we call a proton. And that will go on the Lewis base. So if I draw that as a chemical reaction, there we go, we're splitting hydrogen. Here's our Lewis acid, bar 15. Here's our Lewis base. Too big and bulky to form an adduct, they're frustrated. So I add hydrogen, and then I put the hydride onto the Lewis acid to form a borohydride, and the proton onto the Lewis base to form some protonated Lewis base. And then for 10 years, since that was discovered, people have been using FLPs, frustrated Lewis pairs, to catalyze the addition of hydrogen to all sorts of different substrates and molecules. But nobody had used it for anything else until Andy and I came along. And we pioneered the combination of electrochemistry with frustrated Lewis pair chemistry. And whenever you're going to introduce something new into chemistry, it's a good idea to start with something that's vaguely familiar to people. So we started with the archetypal FLP, where our Lewis acid was this bar 15 I've just shown you, and our Lewis base is this species here. That's just a phosphine. It's a strong Lewis base. And the idea is simple. We're going to take our frustrated Lewis pair and use it to split hydrogen to generate a proton on the Lewis base and a hydride on the Lewis acid. And at the same time as that reaction is going on, we're going to put an electrode in there and oxidize the Lewis acid hydride to extract 2 electrons and leave behind another proton. So overall, we've converted hydrogen into 2 electrons and 2 protons, which is what we want to do. Now, one of the things that Richard Compton taught me was that you better understand the system before you try to apply it. Okay, so we had to work out what the mechanism was. This is the electrochemistry of Bath hydride, right? The solid line's the experimental data, and the open circles are the curves we get when we fit this mechanism and get these parameters out. And the aim of the game is to go around the outside of this circle. So we'd start with Bath hydride, we take an electron out and form this neutral radical species, which spits out a proton and generates this radical anion, from which we take another electron, regenerate our bar 15 Lewis acid, add some more hydrogen, and then round and round we hope to go. Except there are these 2 side reactions, right? When this spits out a proton, that proton isn't bound to a Lewis base. It's not like the proton we get from splitting hydrogen. It's more reactive. And that can react with some incoming borohydride and protonate the hydride off and regenerate hydrogen. And that's not a problem because we can feed the hydrogen back in, but it reduces the efficiency of our cycle. The big problem is this intermediate here, this radical anion. It's very reactive, and it rapidly reacts before we can regenerate the Lewis acid and decomposes. But this is only the first system that anybody had ever tried combining electrochemistry with FLP chemistry, right? So we didn't expect it to be perfect. Does it work? Well, this is the voltage you need to oxidize hydrogen on a carbon electrode. And this is the voltage you need to oxidizing it using our electrochemical frustrated Lewis pair. So we've reduced the voltage, decreased the voltage by over half a volt, by 0.6 volts. Okay, and that's not bad, right? It's a promising start. But we'd already identified some issues. This FLP cleavage of hydrogen is very slow, right? It takes several hours, sometimes several days, to split the hydrogen. Whereas the electrochemistry is much faster, it takes a few minutes or a few hours. So there's a mismatch in the rates. And then we've got these side reactions that regenerate hydrogen and make our system non-recyclable. But that's not bad for a first attempt, so we published it in a pretty good journal, the Journal of the American Chemical Society, 2 years ago. And then we did what synthetic chemists do. We started trying to tune the system. So we switched our Lewis acid to a different Lewis acid. Right? This is a positively charged borane called a Borenium. Okay? And Doug Stephan, the founding father of FLPs, had already shown that with our phosphine, this splits hydrogen to give us now a neutral borohydride and a protonated Lewis base. And it's dead easy to make that hydride. And when we looked at the redox chemistry, lo and behold, we can oxidize that borohydride, take out 2 electrons and a proton, and we regenerated the Lewis acid, and we can see that because we can see it being reduced here. And the question was, is it any good? And the answer was, yeah, it was better than our first system, right? So remember, the aim of the game with these graphs is the peak should go up and move to the left. So this is the direct oxidation of hydrogen on a carbon electrode. And at the same concentration, this is the peak that we get when we use our bar 15 FLP. And it goes up and it moves by over half a volt. But with our Borenium system, for the same concentration, we get a bigger current. And now we've decreased the voltage required to oxidize hydrogen by almost 1 volt, by 0.9 of a volt. Now, in the game of electrocatalysis, shifting a potential, a voltage, by a couple of hundred millivolts is usually a big deal. Right? So shifting it by nearly a volt was pretty good. And we looked at the mechanism of this, and we found that some of those side reactions were less problematic and others were worse. And the real question was, could this catalyst be regenerated? Could we recycle it several times? So what we did was we took our Borenium, our Lewis base, and we bubbled hydrogen through it. And then we oxidized all of the borohydride that we'd made and measured the charge pass. And that just tells us how much of our borohydride we've made. And then we put some more hydrogen into the cell, and we bubbled it through for a little bit of time to regenerate the borohydride. And then we oxidized that again, and we got about 75% of our catalyst back on the second cycle. And then on the third cycle, it had died. So it turns over as a catalyst twice. And we need it to turn over billions of times. But this was only the second system we'd ever studied. So it wasn't a bad start. So we published that, and we were sitting pretty. And then we did what catalytic chemists always do. They find a catalyst, and then they spend several years or even several decades tweaking and tuning the structure of that catalyst to try and make it better, to find out that the catalyst they started with was the best catalyst in the first place. And that's exactly what we've done. We've made over 20 different boron-based Lewis acids, boranes and boreniums. Many of them are new to science, and we've got pretty good at putting different groups around the borane at will. And now we understand from a systematic study how when you change their structure, you change their electronics, and that changes their behavior as a Lewis acid. And so we published a lot of work on that, but we found no magic bullet. Right? So of all the boranes we've studied, in general, borane Lewis acids that split hydrogen really quickly as a frustrated Lewis pair have really poor redox chemistry, bad electrochemistry. Whereas those with good redox properties are generally very slow at activating hydrogen. And there's another problem with FLPs that I haven't really touched upon yet, and that is that conventional frustrated Lewis pairs always require you to add this strong Lewis base, these amines and these phosphines I've been showing you. Now, they're electron-rich molecules. They have their own redox chemistry, and they oxidize at around about the same potential as our borohydrides, which causes all sorts of problems and generally kills the system. But the biggest problem of all, and this is well known by catalytic chemists in the frustrated Lewis pair arena, is that conventional FLPs are invariably intolerant of water. Water either kills the Lewis acid and stops it working, or it kills the Lewis base and stops that working, or more usually it kills both. And yet we want to use it in an application where, well, our net product that we want to make is water. So at this point, things were looking pretty bleak, and I must admit I had my doubts as to whether I'd made the right decision to move fields and abandon my old haunts of chemistry. But I shouldn't have despaired, because I work with a team of really, really excellent chemists. And Andy made a breakthrough. And as is usual in science, whenever somebody makes a big breakthrough, there's usually two people that make it at the same time, but independently. And that's exactly what happened here. Andy and Doug Steffen, the founding father of FLPs, simultaneously but independently discovered that you can get very fast hydrogen activation if you don't add a Lewis base. If instead you use a coordinating, i.e. not frustrated, everyday organic weakly Lewis basic ether solvent. So Doug took our familiar BAF15, and that's known to react with diethyl ether, a common organic solvent, and it's been known for decades to make this BAF etherate classical Lewis adduct. It's not frustrated. In fact, that's how we make BAF, from BAF etherate. But when Doug showed this to some hydrogen, he found that in a couple of minutes, he cleaved it with no added Lewis base. And at the same time as he was doing that, Andy was taking the same Lewis acid, BAF15, but with a different common everyday organic solvent, 1,4-dioxane, and that's been known for decades to form this dioxane BAF adduct. But when Andy showed it some hydrogen, very rapidly we split it. And so they both published their work in one of the top journals in chemistry, and they published it back to back, so the page numbers run on, but Doug, being the more famous name, the founding father, he went first. And so Andy and I together have now developed a whole range of different Lewis acids and different solvent systems, all of which will split hydrogen not in 4 hours or 12 hours or 5 days, but in less than 5 minutes. And the key to this is reducing the frustration. Okay? This is one that we've been working on. We discovered this one in our labs, and it's an interesting one. It's different to all the others, because all of the others produce these terminal borohydrides, where the hydride's on one borane Lewis acid. This one, which is called BAF18, this splits hydrogen, and it forms this bridging hydride intermediate, a hydride shared equally between two Lewis acidic boranes. And I'll come back to that in just a moment, because that's going to be important. Andy and I took our solvent-FLP idea a little further and made FLPs water tolerant, right, last year. The trick is simply to use pressure, right? So now we started pressurizing our systems to 50 times atmospheric pressure of hydrogen. It works because the reason water kills our Lewis acid, or one of the reasons it kills Lewis acid, is water can bind to the borane. And in a conventional frustrated Lewis pair, you would have a strong Lewis base hanging around. And that Lewis base can then take a proton off the water and form this species, hydroxyborate. And as soon as you form hydroxyborate, that's a thermodynamic sink. There's no coming back from it. Your catalyst is dead. But we don't have a strong Lewis base in our system. We've got our solvent, right, which can displace water for a start and set up an equilibrium. But even if the solvent was a strong enough Lewis base to take off the proton, and it's a pretty weak Lewis base, it forms a protonated solvent molecule. And that's quite a strong acid, and it's strong enough to put the proton back onto this hydroxyborate and resurrect it from the dead to make the water adduct, and we kick the water off with this solvent, which is in vast excess. So avoiding strong Lewis base is good, but adding hydrogen at higher pressure pulls this equilibrium to give us this product, the borohydride, and that's what we want. So that pulls the equilibrium all the way over, so we don't make anything that we don't want, and we're favoring the formation of what we do. And then we add our substrate, in this case this was acetone, and we add hydrogen across this carbon-oxygen double bond, first the proton then the hydride, and we form propanol, isopropanol. And that works even when there is 5 times as much water present in this system as there is Lewis acid. And that was the first time that we'd ever got an FLP catalyzed reaction to be tolerant of water. So we can use that on the open bench, we can use wet solvents, and that solved a lot of our problems. But, and this is where we have to call in some help from the organic chemists, the big problem, right, was we'd solved this problem of having these strong Lewis bases that were redox active and these strong Lewis bases that were making our systems water intolerant. We'd solved all that. But the thing we hadn't solved was this difficult redox chemistry of our boranes, the fact that they made unstable things that decayed. And so I got an email one day from this chap. This is Dr. Michael Ingleson at Manchester University. And although this slide says organic chemistry to the rescue, I should point out he is actually an inorganic chemist and an expert in frustrated Lewis pairs. And like Andy and I, he's also a Royal Society University Research Fellow. And his research group were the first team to report frustrated Lewis pair activation of hydrogen, not using an inorganic borane, but using an organic molecule, a carbon-based Lewis acid called N-methyl acridinium. That's N-methyl acridinium, right? And what Mike showed was if you add that to a Lewis base, this is lutadine, right? That will split hydrogen. We'll put hydrogen onto this carbon atom here and put a proton onto the Lewis base. And acridane and acridinium, this is acridinium, this is acridane, they're dead easy to make and they're dirt cheap. And the acridinium system resembles quite closely one of the structures found in NAD+. This is used in our bodies in biology as part of the energy respiration cycle, right? And whenever you get a catalyst that starts to look like something in biology, you know you're onto a winner, because biology's had 4 billion years to get their chemistry right, so they're way ahead of us. Right? And also, this carbon Lewis acid is tolerant of air and water. So this is the carbon-based Lewis acid. We've got a positive charge on this carbon atom here, and we add a hydride to it. When we split hydrogen, that goes on there. So this is acridinium, and this is acridane. And I've labeled this 1+ and 1H in this mechanism here. And the redox chemistry for the oxidation of acridane is brilliant. Right? Here it is. There are none of these side reactions that plague the inorganic boranes. No side reactions. I'll spare you the details, but the other good thing for me personally was I didn't have to work out the mechanism. A very famous electrochemist called Savion had already done it for me in the 1990s. That made my life easier. I won't bore you with the mechanism, but the overall net result is you take acridane and we oxidize it and we regenerate acridinium, our Lewis acid. We take out 2 electrons and we form a proton. That's exactly what we want. There are no side reactions going on. So this was brilliant. I thought, yeah, here we go. Except it's pathologically slow to split hydrogen. It takes 9 days. Okay, that's never going to work for our system. So then it was back to the drawing board. And inorganic chemistry came to our rescue. Remember I told you about this BARF18 that we had that was a bit odd? Okay, either as a solvent-FLP or in this case with a strong Lewis base, tetramethylpiperidine, a conventional FLP, it splits hydrogen and it is the only borane we've ever found that when it does that forms this bridging hydride species here, right, which is H-BARF18 twice. And we can even isolate and crystallographically analyze this. Ignore all the chemical shrubbery. The key features are these 2 boron atoms in pink from the 2 Lewis acids, and sandwiched in between them is this white hydride. That's the bridging hydride in there. Now this cleaves hydrogen really, really quickly. It's brilliant at cleaving hydrogen. But when you want to oxidize this bridging hydride, it's awful. Right? It takes more energy to oxidize this bridging hydride than it does to just oxidize hydrogen directly. But then I had a cunning plan. A plan so cunning you could put a tail on it and call it a fox. I'm going to take my borane, which is really fast at splitting hydrogen but has dreadful redox chemistry, and I'm going to combine it with my carbon-based Lewis acid, which is really bad at splitting hydrogen but has brilliant redox chemistry. I'm going to put them together. Right? So my borane, BARF18, with my lutadine Lewis base is going to split hydrogen and form this bridging hydride species. Lutadine is a good Lewis base to use because it doesn't have any redox chemistry in the area that we're interested in. It doesn't interfere, doesn't get in the way. That BARF18 bridging hydride is then going to act as a hydride shuttle, right? It's going to transfer the hydride from hydrogen onto this acridinium carbon-based Lewis acid and generate our acridane. And then we're going to oxidize our acridane with some more lutadine to get a proton and 2 electrons. So overall, hydrogen in, 2 protons on the lutadine coming out, and 2 electrons. And that's what we want. So the biggest question was, will the BARF18 hydride transfer the hydride and work as a hydride shuttle? Will it transfer it to acridinium? And this is data from a technique called nuclear magnetic resonance. Don't worry about what that means. It simply allows chemists to look at the structure and count atoms in a molecule. And most molecules have a characteristic set of these signals that we get. And this is the signal for pure acridinium, our carbon-based Lewis acid. And this is the signal you get for the acridane when we put the hydride onto the acridinium. And we get a different set of peaks highlighted in blue. So when we took acridinium, right, with our Lewis acid, our BAF18, Lewis base, and added some hydrogen, we see that we don't have any acridinium signals left, and instead we start to see these acridane signals. So the BAF18 was transferring the hydride onto the acridinium to form the acridane. And we could monitor the growth of those peaks and work out the conversion of acridinium to acridane. And after about 20 minutes, about 45% of the acridinium has been converted to acridane. So that was pretty good. So here I'm going to summarize a whole week's worth of data for you of experiments. Right? We have a solution. It's got acridane in it. It's also got our BAF18 and our lutadine. We're going to bubble hydrogen through, we're going to oxidize all of that acridane in the solution and measure the charge passed. And that's the dotted line. That's the 0 point. Once we've oxidized the acridane and formed all the acridinium, we're then going to bubble hydrogen through it for 20 minutes, regenerate the acridane. Then we're going to oxidize that acridane and work out how much we get. And on the first run, we get about 45–50% of our carbon-based Lewis acid catalyst back. And then we bubble some more hydrogen through and regenerate the acridane, and we oxidize it, and we got about the same amount back. And then we repeated that 3 or 4 times, and gradually the amount of our acridane that we were producing in our system, the amount of our catalyst we were getting back, was decreasing. But we realized very quickly this is only 1/2 of a fuel cell. It's the hydrogen oxidation half. It's the bit that generates protons. There's no reaction in this system that consumes protons. And every time we split hydrogen, we put a proton on the Lewis base, lutadine. And every time we oxidize acridane, we put another proton on another lutadine molecule. And so what had happened here was we basically just run out of Lewis base. So then what we did was we added some more lutadine before we bubbled it for hydrogen, and lo and behold, we got exactly the same signal back as we had in the first place, and our system was back in action. Then that was a Friday afternoon, so then we, instead of bubbling hydrogen for 20 minutes, we bubbled hydrogen over the weekend, sealed it under hydrogen, and we came back, and then we wanted to oxidize all of the acridane we generated, and now when we did that, we got more acridane than we ever had to start with. Sounds a bit weird. What's happening is the amount of that bridging BAF18 hydride had built up in the solution over the weekend. So every time we were oxidizing the acridane at the electrode, there was more hydride there to regenerate it. So this is true electrocatalysis. We're turning over in real time during the experiment, and so we get a much larger, truly catalytic current. We oxidized all that, bubbled the hydrogen through for 20 minutes, got our same signal back. And on the 8th cycle, it had died. It had been going for a week, this experiment, and some water had crept in over that time. And it had killed the BAF18 borane catalyst. It hadn't touched the carbon-based Lewis acid because when we add some authentic borohydride to it, we got exactly the same signal back as before. Right? So we published that work in one of the top Royal Society of Chemistry journals just 3 weeks ago. And I guess it's kind of a eureka moment. The idea of combining inorganic FLPs with carbon-based Lewis acids really worked. Okay? We decreased the voltage needed to oxidize hydrogen by over 1 volt. Right? That was pretty good work. We got these large catalytic currents obtained. When we looked at how fast the hydride transfer from the borane to the carbon was going, it's 27,000 times per second. Well, that's reasonably fast. And we showed that our carbon-based Lewis acid was tolerant of both water and these common impurities that we find, both carbon monoxide and carbon dioxide. So with this catalyst, unlike platinum, you don't need any ultra-high purity fuel gases. You can breathe air, and you can work with any old dirty grade of hydrogen that you like. And the only slight fly in the ointment is we're trying to work at the moment to develop some more water-tolerant boranes and some solvent-FLP systems to fix that little problem we had with the water. Right, so we are using this. My group, in collaboration with Andy and Mike, we're the only group in the world, here at UEA, we're the only group in the world developing frustrated Lewis pair catalyst for fuel cells, right? Like our hydrogen fuel cell cars. All right, so let's dim the lights a little bit. I asked the funding councils for an Audi R8 supercar, because I like fast cars, yeah? And they said no. So my postdoc, James, bought me 3, but not quite what I was after. This is one of our hydrogen fuel cell cars, right? It's a battery fuel cell electric vehicle hybrid. The batteries supply the acceleration and the sports car performance, and the fuel cells recharge the batteries. And they work, right? And we can have a little play with these in the foyer later, and we'll have some drifting competitions and some races. Where's my pointer? Right. Yep, so that's my research group looking like French special forces down at our special secret Top Gear test track. That was, I'm very modest, that was me winning. Right, and it's not just energy generation that we're using FLP catalysts for, right? We're also developing energy storage technologies. And this is what Rick Osterloy, the president of Motorola Corporation, has to say. He said, everyone in the world, consumers and all the manufacturers would benefit from some unforeseen breakthrough in battery chemistry technology. At the moment, everyone is getting interested in incremental, tiny benefits from changes in lithium-ion batteries, but fundamentally there hasn't been a Moore's law type curve for battery improvements, and I think that would be something everyone would benefit from. Moore's law is how the rate of computing power increases with time. That's not happening for battery chemistry. For 216 years since Alessandro Volta, for whom the unit of volt and voltage is named after, invented the first battery with these copper and zinc plates, all battery chemistries have essentially used redox-active metals to store electrical energy. And the lead-acid battery is the current global market leader in the rechargeable battery market. It's got 80% market share, and it uses toxic heavy metals like lead and horrible things like sulfuric acid. And it works as a battery because it stores a difference in charges, right? This is lead in the +4 oxidation state versus lead in the 0 oxidation state when it's fully charged. And when it's fully discharged, we've got the same charge on both sides, lead 2+. And the last new battery chemistry was introduced over 30 years ago, in fact, in the year I was born, when John Goodenough pioneered the way forward for the lithium-ion batteries that now power all of our wonderful smartphones and laptops and tablets, etc. And these store charge by inserting lithium ions in between the carbon sheets, the graphite sheets in a carbon electrode. And that was the last time any new battery chemistry was really introduced. Until now. We're developing these frustrated batteries where we take an electrode bearing our Lewis acid and another electrode bearing our Lewis base, and they will split hydrogen. And when they do that, you end up with one electrode that's negatively charged and one electrode that's positively charged. You've got a separation of charges, which equals a voltage, which is a battery in its charge state. So we are now currently developing frustrated batteries. This is a brand new battery chemistry, and the first battery chemistry that I know of that doesn't rely on any redox-active metals. Instead, it's recharged by hydrogen, and not hydrogen gas, before you get worried. This is hydrogen dissolved inside the solution in the battery. So it's the first new battery chemistry for 30 years, I reckon. And it's the first battery chemistry for over 200 years that is entirely metal-free. No toxic heavy metals, no environmentally worrying metals, just hydrogen. I can't tell you about the chemistry of this because we're currently in the process of patenting it, but I can give you a sneak preview to see if it works. Right? So this is a Blue Peter one that we made earlier. And if you look very carefully, you will see, that's not my laser pointer, oh, there you go, it lights up this green LED. To do that, it has to have a voltage of at least, what, 1.2, 1.9 volts? Something like that. And we can charge and discharge our battery multiple times, and everything is good. Now, I've had instructions, we've all had instructions from on high, that whenever we give these public lectures, we should emphasize where we're from, right? The University of East Anglia. I love the University of East Anglia. Ever since I moved here, it was the best decision, other than marrying my wife, I think I ever made. I'm guessing most of you here tonight know where UEA is, right? But for the benefit of those watching on YouTube, yeah, the University of East Anglia is here, in the east of England, in the fantastic city of Norwich, one of the nicest cities to live in England. And it's one of the top 150 universities in the world. And it's one of the top 10 universities conducting research in the United Kingdom. And not many people seem to understand that. And in terms of the quality of our education, we're the second best university in the United Kingdom for how we teach our students and how happy they are with how we teach them. And the School of Chemistry at UEA, and again, not many people seem to know this, in terms of the quality of the research that we publish, we are the 4th best chemistry department in the country. Right? And we're top 10 for our overall environment of research. And 97% of our students are satisfied with our course because we're starting to throw out those traditional monologue lectures that I've just given to you and replace them with cutting-edge teaching methods supported by the latest research in teaching and the latest technology to support that learning environment for our students. So, if you're thinking of coming to study chemistry at university, or your children are, if you want to be part of the everyone knows that crowd, okay, you'll probably think, okay, a chemistry department at a historic, probably slightly prestigious university is going to be a good chemistry department. And you probably wouldn't think of coming to UEA. And that's fine. Go elsewhere. But if you want to be smart, and if you want to get more bang for your buck in the era of £9,000 a year tuition fees, right, you want to come to one of the best chemistry departments in the country and get one of the best educational experiences in the country, and that means you want to come to the School of Chemistry at the University of East Anglia. Now, this is how I like to work. Since becoming a professor, I am automatically disqualified, no longer qualified, to do any of the work. Okay? I didn't do any of the work I told you about tonight. I just claim all the credit for it. And I think it's time to introduce the real stars of the show, the team of extremely talented and bright young chemists that work for me. So I'd like to introduce my group and say thank you to them for their work. Dr. Elliot, they're all here tonight. I didn't make them come. Dr. Elliot Lawrence, who's been with me pretty much since the beginning and has been behind most of the breakthrough developments in the electrochemical frustrated Lewis pairs. Dr. Robin Blagg, who joined us and brought with him a wealth of synthetic and electrochemical expertise in X-ray crystallography and computational chemistry. Dr. Elian Bennett, who's working on water-tolerant and water-soluble boranes. And for 10 years, since their introduction, we still don't know actually how FLPs split hydrogen. But Elian's work, I think, might just tell us that. I didn't talk about that tonight, but that's what he's working on. Then there's James. He's my PhD student. He has absolutely nothing to do with these frustrated Lewis pairs, but he gets into everything, so he gets in here. Dr. James Courtney, soon to be Dr. James Courtney, I hope, who is our chemical engineer and fuel cell expert and electrochemistry expert and battery expert, and also occasionally helps look after Bonnie, who's our lab mascot. Every lab should have a Labrador. Right? Yeah. Okay, so that's Bonnie. She keeps us all in check. Obviously, I wouldn't be here without my collaborators, so I'll thank them again. Dr. Andrew Ashley and his group at Imperial, and Dr. Michael Ingleson and his group at Manchester. We're still working together, the three of us. We're still building on our collaboration, and we're developing genuine frustrated fuel cells over the coming years. And obviously, we need money to do our research, right? So I'd like to thank the Royal Society for funding my University Research Fellowship and also Andy and Mike's. And the European Research Council, who paid for the lion's share of this research. And I don't want to get into an argument about Brexit, but if Britain wasn't part of the EU, none of this research would have happened. None of it. And I wouldn't be here. Right? This wouldn't be a British breakthrough or invention or discovery or whatever it ends up being, possibly, maybe one day. It'd end up being a German one or an American one. Okay, so I think being part of the EU brings more benefits than disadvantages. I'd like to thank the Engineering and Physical Sciences Research Council and the Leverhulme Trust for additional funding on top of that. And finally, I'd like to thank you all for coming out tonight to listen to me talk. In particular, I'd like to thank some of my colleagues and some of my friends and some of my family who've been there for me through some pretty difficult times in the last couple of years. You know who you are, and thank you.